Good afternoon. I'm Professor Chris Hopkins, Head of Clinical Engineering and the Tritech Institute within Hywel Dda University Health Board, and my good friend and colleague joining us today is Professor Tony Fisher, Head of Medical Physics and Clinical Engineering within Royal Liverpool University Hospital. Tony and I are also part of a wider group who include Professor Paul White, Head of Clinical Engineering up in Cambridge, Professor Fred Madonica, Managing Director of OpenCFD Limited, Peter Bill, Head of Clinical Neurophysiology up in Birmingham, Claire Greaves, Chief Scientist and Clinical Director for the Science and Technology Pathway up in Nottingham, and Frank Mills from the Institution of Mechanical Engineers. Health and care workers are at 3 to 4 times greater risk of developing and dying from COVID-19 than the public. However, measures to reduce airborne spread in high-risk health and care settings, which are critical to the pandemic response, have thus far been inadequate and overlooked. Current policies continue to emphasise the importance of fomite droplet and direct spread, but do not properly address airborne transmission, and it is now established that SARS-CoV-2 spreads predominantly via the airborne route and is readily transmitted in healthcare settings beyond formally classified aerosol generating procedures. In this study of indoor ventilation, sponsored by UK Research and Innovation, using quality assured open source CFD, the efficacy of several ventilation strategies were assessed. These strategies include mechanical, controlled by the building air management systems, natural through opening windows, augmented ventilation from the UV air cleaning devices, and several roof diffuser vent designs.
Thank you, Chris. SARS-CoV-2 singleton virus particles have a major dimension of about 100 nanometers. Dental treatment procedures generate virus-containing particles in the range of 0.1 micron to about 500 micron or 0.5 millimeters. These are initially airborne. We note that particles of less than 5 micron tend to move with massless buoyancy in the air and remain in suspension. On the other hand, larger particles with significant mass tend to precipitate spontaneously under the influence of gravity. We note that due to evaporative water loss, larger particles can lose mass and become buoyant. Our CFD models must account for this. The principal mitigation strategy of airborne contamination is changes of room air, exchanging new clean air for old contaminated air. Here we describe how these changes of room air provided by the building's heating, ventilation and air conditioning system can be augmented by using local air cleaning, employing standalone air scrubbers. Air scrubbers commonly use 2 technologies: simple mechanical HEPA filters and or ultraviolet irradiation. In our work, we disregard HEPA filters, which can become significant biohazards and require frequent high-risk replacement. The effective ACH, or air changes per hour, in a ventilated room fitted with an air scrubber is simply the sum of the ACH from the HVAC system and the airflow through the air scrubber. The effective clearance of contaminated air, assuming perfect air mixing throughout the room, follows a simple exponential decay model. 1 ACH is the time constant. Therefore, 1 ACH gives a clearance of 63%, 2 ACH 95%, and 4 ACH 99.5%. This is the familiar law of decreasing returns. We define clearance as the fractional change in contaminant concentration as a percentage. The infection control and microbiology communities use the term log reduction, which is defined as a negative log in the change of contaminant concentration. The time taken to achieve a log reduction of 3 or 99% clearance is often taken as an index of ventilation efficiency. The dynamics of clearance is shown in the following slide for a range of ACHs.
There are a number of suboptimal UVC air sterilising devices on the market, and it's important to recognise that we do not endorse the use of plasma or ozone emitting devices as per the current advice from SAGE. The Mansfield Pollard U-vent was recommended for use within our acute sites as it's already been reviewed by colleagues in Liverpool. The U-vent is a small mobile operating unit operating at 250 nanometers with an air volumetric flow capacity of 180 cubic meters per hour on standard settings and 360 cubic meters per hour on boost. Mansfield Pollard claim a sterilisation rate of greater than 97.6% within a 50 to 80 cubic metre environment, citing validation work at the Universities of Leeds, Bradford and Public Health England, Porton Down. The room dimensions need to be calculated in order to determine the optimum number of devices required, and assuming you place these devices appropriately within the room area, the number of air changes per hour can be supplemented through the use of these air scrubbers, assuming of course that good mixing is taking place. A number of the Mansfield Pollard U-vents were introduced onto our SARS-CoV-2 ward within Withybush Hospital in West Wales. The UVC sterilisers were strategically placed within each of the single occupancy 4-bed and 5-bed areas with overall room volumes of less than 50 cubic metres. Initial feedback from the clinical teams were that they were quiet to run, staff could still work in the bays with no impact upon nursing staff or working around them, ergonomics were good, patients could sleep comfortably with them on, and patients walking could see them in the bay with no trip factors for dementia patients. Quantifying the rate of far UVC viral inactivation within a general room is complex and multiphysics in nature. The application of CFD modelling to the understanding of the complex and isotropic airflows associated with fixed and moving objects, including humans, can suggest effective optimizations of air changes per hour strategies, achieved by combining air scrubbing with pre-existing ventilation. Our computational fluid dynamics models provides information on the dispersion of airborne particles in healthcare environments where AGPs present a significant risk. CFD is a useful tool to understand the dynamics of infectious particles through the air. It has been used successfully to study the effect of different ventilation regimes and layouts within clinical areas. Here we can see the difference on the age of air within a room environment. On the left we see room clearance with no air scrubber present, and on the right we see air clearance with the air scrubber present on normal setting of 180 cubic meters per hour. It is noted that the current HDM 03-1, which is the specification for ventilation in UK hospitals, recommends 10 air changes per hour for treatment rooms, and that the selected room at Withybush was only capable of delivering 50% of this target. This issue is relevant across many trusts and health boards, which have old, established facilities constructed before the current HDM 03 was issued. Measurement of airflow rates will confirm which areas achieve current standards and which fall short and should be upgraded. It is further noted that the requirements of HDM 03 are not retrospective. Operating in the room at 5 air changes per hour means that dilution of viral load will take longer, and consequently a fallow period has to be allowed between procedures to give time for ventilation to change the room to a satisfactory clean level. Here we can see the difference on the age of air within a room environment. On the left we see room clearance with no air scrubber present, and on the right we see a further improvement in air clearance with the air scrubber present on its boost setting of 360 cubic meters per hour. When we consider endoscopy or dental rooms, in order to reduce the requirement for the long fallow periods, typically 20 minutes, which essentially limits the number of patients that could be seen in a clinical session, it was necessary to introduce measures to raise the equivalent air change rate from the current 5 air changes per hour to over the minimum 10 air changes per hour as stated in HDM 03. This was carried out by installing a mobile UVC unit into the room which provided the equivalent of 7 air changes per hour of recirculated air, leading to a total equivalent of 12 air changes per hour, i.e. 5 air changes of outdoor air supplied by the mechanical ventilation system and 7 air changes per hour of recirculated and clean sterilised air supplied by the UV mobile unit. When the UV sterilizer was introduced into the room, there was a reduction in fallow time by up to 75%. On standard settings, 180 cubic meters per hour, the age of air within the room reduced to 6 minutes, and on the purge or boost setting of 360 cubic meters per hour, this was further reduced down to 4 minutes. Similar studies in well-ventilated rooms of different sizes and ventilation strategies suggest a close link between the ventilation rate, air changes per hour, and mean AOA as an absolute measure in minutes. Positioning of UVCs or direction of airflow gives only plus or minus 15% variation in the clean air mixing.
Chris's previous CFD graphics show the dynamic development of clearance. Here, in this slide, we map the interaction of particles ejected from the mouth of a patient during their dental treatment onto airflow streamlines. We note that the heavier AGP particles tend to precipitate out spontaneously onto the patient's chest bib and make a relatively small contribution to the contamination of room air. We think this is a very significant finding. This, of course, is a very busy slide. Here we compare the relative clearances obtained by a combination of HVAC modifications and air scrubber configurations. In summary, for the average age of air index, the optimal combination of minor HVAC mods and air scrubber implementations achieves reduction from 600 seconds to 250 seconds. This implies for a given clearance, interpatient fallow times can be reduced by approximately 60%. We have built a simple to use web tool to calculate room clearances and how they may be improved by the use of ultraviolet air scrubbers. The web link and some example designs are described in the next few slides, which colleagues are invited to browse from the slide pack that will be available from this conference.
CFD modelling suggests a significant improvement in clean air after introduction of the UVC sterilisers. An early work with the PCR detection method for SARS-CoV-2 seemed to confirm this. The improvement is seen in both age of air and air mixing when placed in an optimum position with no significant issues raised from a real-world testing perspective. There is ongoing work with Public Health England, the CSO office in England and SAGE to develop this research further, while supplementing this with biovalidation work. Many thanks to you all for listening today, and we hope you enjoy the rest of the conference.